Dr. Naibin Sebastian for the very kind invitation to be a part of this wonderful event online, the MATCON 2021. So it would have been nice if I physically there at CUSAT for multiple reasons. So I can see several of my friends at CUSAT, Professor Srikumar, and some of my colleagues, friends, and yeah, because of this unprecedented situation. Now we are all passing through, we have to restrict ourselves in our office. Yeah, so today in the next 45 minutes, I will try to give you a take-home message on one aspect of our research on which is centered around carbene catalysis. So basically, organocatalysis using N-heterocyclic carbenes. So we know that carbenes are highly electrophilic species. So in general, carbenes having a divalent nature. So it is highly electrophilic in nature because it is having a sextet of electron, highly reactive species because of this, and hence it is a very short-lived species. And when we think about carbenes in general, the first thing that will come to our mind is carbenes are having sextet of electrons, so it needs 2 more electrons to complete its octet. Or in other words, carbenes in general are electrophilic in nature. Typical examples are dichlorocarbenes or dicarboethoxy carbenes, where one can represent the carbene like this, which are electrophilic in nature or electron-loving species. On the other hand, there are a species of carbenes which are electron-rich species, so which is otherwise known as the nucleophilic carbenes, where a carbene center is flanked by heteroatoms such as oxygen, nitrogen, or sulfur, where the mesomeric effect of this heteroatom, which pushes the electron density towards the carbene center, thus making the center more nucleophilic instead of the inherent electrophilic nature. So this type of carbenes are known as nucleophilic carbenes, where the carbene carbon is relatively electron rich because of the presence of the heteroatom at the vicinity. By virtue of the mesomeric effect, this heteroatom pushes the electron density towards the carbene center, thus making the carbene carbon more nucleophilic. So if such a carbene center forms the part of a ring, then we get an N-heterocyclic carbene. So nucleophilic heterocyclic carbenes. So the nucleophilic heterocyclic carbenes are nucleophilic species. So the electron-rich species, which act as nucleophilic species in carbon-carbon or carbon heteroatom bond-forming reactions. And this can be of different types: the imidazole-derived system, the thiazole-derived system, or even the triazole-derived system. And one can generate these carbenes in solution from the corresponding azolium salts, either the imidazolium salts, thiazolium salts, or the triazolium salts, by treating these species with a mild base such as potassium carbonate or even potassium terbium or nucleophilic bases such as DBU, DMAP, DAPCO, etc. So because of this azolium nature, the nitrogen is cationic, and this CH proton is highly acidic, so that a mild base can abstract this proton, and this can lead to the formation of this carbene in solution. So one of the most important applications of these carbenes in organic chemistry is the remarkable ability of these carbenes to donate this electron pair, thus acting as a wonderful ligand in transition metal catalysis. For instance, we know the Krebs second generation catalyst. So the carbene is a ligand for ruthenium in the second generation metathesis catalyst. So in a different domain, carbenes are also used in another area of catalysis. So we know that catalysis is one of the fundamental or sustainable methods for forging carbon-carbon and carbon heteroatom bonds. So among the various methods where one can do catalysis, for instance, starting from the enzyme catalysis or the biocatalysis, then the second one being the transition metal catalysis, and the third is the new domain, which is otherwise known as the organocatalysis. There is a catalytically active species, which is otherwise known as the carbenes, which we are talking about. this can lead to unconventional ways of forging carbon-carbon or carbon heteroatom bonds. I will tell you in more details how it can do these unconventional modes of carbon-carbon or carbon heteroatom bond forming reactions. So this carbene-based organocatalysis is one of the area of small organic molecule-based catalysis, because it is completely transition metal free or transition metal free modes of doing catalysis. So one of the fundamental methods where people find application of carbenes in organocatalysis is the remarkable ability of this nucleophilic species. I told you this is nucleophilic in nature, and because of the nucleophilicity, it can add to electrophilic species such as an aldehyde, which could lead to the formation of this tetrahedral intermediate. The anion, the tetrahedral intermediate can pick a proton. This happens mostly in an intermolecular way, leading to the formation of an enamine intermediate. So this is having an enamine moiety. So the aldehyde carbon now changed the polarity from the inherent electrophilic nature to the nucleophilic nature. Or in other words, one can represent this intermediate, which is otherwise known as the Breslau intermediate, which was first demonstrated by Ronald Breslau from Columbia as early as 1958. The ability of this carbene species, this catalytically active species, to reverse the inherent mode of polarity and hence the reactivity. For instance, in the case of aldehyde, the electrophilic nature has been converted into a nucleophilic nature. And this concept is, or this phenomenon is known as the Umpolung, or the polarity reversal process. So carbenes, when it adds to the aldehyde, the inherent electrophilic nature has been changed to the nucleophilic nature, or one can easily represent it as a formal acyl anion equivalent. So once the acyl anion is generated, it can add to a different aldehyde in a process which is well known for a carbon-carbon bond forming reaction, the benzoin condensation, or it could add to an electrophilic carbon-carbon double bond, a carbon-carbon double bond which is attached to an electron withdrawing group, to form a variety of 1,4-dicarbonyl compounds via a carbon-carbon bond forming reaction, which is known as the Stetter reaction. So this is the fundamental mode of reactivity of carbenes in organocatalysis. And I hope I was able to tell you that this is one of the way carbenes can do unconventional mode of carbon-carbon bond forming reaction. So the way carbenes can change the polarity of aldehyde from the inherent electrophilic nature to the nucleophilic nature. So this is just a prediction in 1958 by Breslau that these reactions proceed via the enaminol intermediate. But as early as 2013, the Berkesel and co-workers, they have even the crystal structure of this conjugated Breslau intermediate and the simple Breslau intermediate and all sort of carbene adducts from aldehyde. It is now stable and one can have the crystal structure of this Breslau type intermediates. So when we started working in this area of carbene catalysis, so the underlying principle is the carbene generation in solution from the azolium. It adds to the aldehyde, forming the tetrahedral intermediate, thus the Breslau intermediate generation via a proton transfer. So the addition of this Umpolung species, so the acyl anion intermediate, to vinyl sulfones or vinyl phosphonates, which are moderately electron poor acceptors, which is unknown at that time. So in 2012, we demonstrated the addition of a variety of aldehydes to vinyl sulfones. So the idea is we started with a thiazolium salt. Using potassium terbutoxide as a base, we can abstract this proton and this carbene can be generated. The carbene can reverse the polarity of this aldehyde from the inherent electrophilic nature to the nucleophilic nature, and this could add to the vinyl sulfone to form a variety of gamma keto sulfones in high yields. So this process has been also extended from vinyl sulfones to vinyl phosphonates. So these are two classes of compounds which are relatively electron poor species. So the addition of a carbene generated from the imidazolium salt to this aromatic aldehyde, making it now nucleophilic in nature species, and then add across the vinyl phosphonate to form a variety of gamma keto phosphonates. So as I told you, the foremost mode of reactivity of carbenes in organocatalysis is the ability to add to aldehyde and thus reverse the polarity to generate the Breslow intermediate. So this concept can be extended from a simple aldehyde to an alpha beta unsaturated aldehyde via introducing a vinyl group. So simply changing an aromatic aldehyde to cinnamaldehyde derivatives, where one can again add this carbene to this aldehyde, thus generating a conjugated Breslow intermediate, which is nothing but a homoenolate intermediate, which this chemistry is pioneered by Geoffrey Baudet and Glory's labs from the Europe. So we use this concept for the construction of a coumarin derivative, indeed a highly diastereoselective synthesis of this type of cyclopentane fused coumarins, via the generation of the homoenolate from this enol and carbene and addition across a hydroxychalcone to form a variety of coumarin derivatives in high diastereoselectivity. And this chemistry has been extended to enoyl pyridines, where one can synthesize relatively interesting cyclopentane fused beta lactones in high diastereoselectivity and broad scope. So as I told you, carbenes are very much known for the umpolum reactivity, where the polarity of aldehydes can be changed and alpha beta unsaturated aldehyde can be changed. So this concept, or the umpolum concept, is in majority of the cases, this polarity reversal is limited to aldehydes, but it is little bit known about the polarity reversal of Michael acceptors or an activated ketones, such as an alpha beta unsaturated ester. As demonstrated by Fu and co-workers, so we know that this alpha beta unsaturated ester is inherently electrophilic at the beta position. But using addition of a carbene to this species, the polarity can be reversed to the nucleophilic nature, just like the aldehyde polarity reversal. And once this polarity is changed to nucleophilic nature, this can displace this bromide to form a new carbon-carbon bond or an exocyclic cyclopentane derivative. And this concept was initially limited to the intramolecular reaction, which was extended to intermolecular version via a tail-to-tail dimerization of these methacrylate derivatives to form again a new carbon-carbon bond. So one acts as a donor, one acts as an acceptor to form a new carbon-carbon bond. And these reactions are envisioned to proceed via the deoxy analog of Breslow intermediate. So remember, in the case of aldehyde, the addition of carbene leads to the Breslow intermediate, but in the case of a Michael acceptor, it is a deoxy Breslow intermediate. So we envisioned that can we extend this concept from the well-known concept of aldehyde umpolum and relatively known concept of the Michael acceptor umpolum? Can we extend this beyond these electrophiles? So we came up with this idea of polarity reversal of aldemenes specifically. So whether we can do the umpolum of aldemenes. So we came up with this imine substrate. So the idea was to reverse the polarity of this imine. So we know that this imine is inherently electrophilic in nature. So can we change the polarity of this imine to nucleophilic nature? And if successful, this nucleophilic species can add to this Michael acceptor to form a 2,3 disubstituted indole derivative. And if successful, this reaction could proceed via the ASA analog of the Breslow intermediate. So instead of this simple Breslow intermediate, we can have the ASA analog of Breslow intermediate. So this was the idea. So my student Atanu Patra, so he came up with an aldimine substrate, which is connected to a Michael acceptor using a benzene tether. So a 1,2 disubstituted benzene derivative. And we treated it with a N-phenyl substituted triazolium salt in presence of potassium terbium to generate the carbene at this position. And after a series of optimization studies, Atanu found that this reaction indeed works quite well in DMF as a solvent at a relatively high temperature. And these 2,3 disubstituted indole derivatives are formed in moderate to high yield in broad scope. As you can see, this reaction tolerates a broad range of functional groups, a substitution at a variety of positions of the aromatic aldehyde as well as the heteroaromatic aldehydes. And in all the cases, the products were formed in moderate to good yield. So we believe that this reaction proceeds via the generation of the free carbene as usual from the corresponding azolium salt in the presence of a base. So the base abstracts this proton to form a nucleophilic carbene, and the carbene adds to the imine moiety to form a tetrahedral intermediate, which undergoes a proton transfer to generate the key Asa-Brislow intermediate. At the same time, we also considered the possibility of a carbene addition to the Michael acceptor moiety of the imine substrate, thus leading to the generation of the deoxy-Brislow intermediate. And this deoxy-Brislow intermediate can add in an intramolecular fashion to the imine moiety, thus leading to the formation of the same product. However, our initial mechanistic studies followed by DFT calculations done by my friend Kumar Vanka from NCL Pune, we found that this reaction indeed proceeds via the Asa-Brislow intermediate and not the deoxy-Brislow intermediate. And once the Asa-Brislow intermediate is generated, it could add to the activated carbon-carbon double bond to form a cyclic compound, the enolate intermediate, which can undergo a proton transfer and an elimination of free carbene to lead to the formation of the 2,3-disubstituted indole derivative. So it was very good. This was the first demonstration of the polarity reversal of an imine substrate using carbene as an organocatalysis. Although these carbenes are well known for the umpolung of a variety of aldehydes and a series of activated carbon-carbon double bonds. So with this interesting result, we thought we can extend this concept beyond 2,3-disubstituted indole derivative. So my student came up with a substrate, again, an aldimine substrate, which is connected to an alpha trifluoromethylated styrene derivative. And under a slightly different condition, instead of an N-phenyl triazolium salt, we use an N-mesithyl triazolium salt using DBU as the base instead of potassium terbutoxide. Atanu was able to get a 1,3-dis or disubstituted, or specifically 2,4-disubstituted quinoline derivatives, in this case in moderate to good yield and with broad scope. I'm just showing the selected examples of this series. So far we found that this umpolung concept of these aldimines essentially works for the synthesis of a variety of indoles and quinoline derivatives. Although we thought, or we considered, the addition of carbenes to the Michael acceptor, thereby generation of the deoxy-Brislow intermediate. To convincingly prove that the imine umpolung is happening, we came up with another substrate, a bis-imine substrate of this type. And the idea was, again, the addition of carbenes. In this particular case, we thought of demonstrating an enantiomerically pure synthesis, or enantiomerically or asymmetric catalysis, or enantioselective catalysis using chiral and heterocyclic carbenes. So the idea was to use one of the imine moiety for the addition of carbenes and use the second imine moiety for the acceptor of the Asa-Brislow intermediate. So Tamal Kandidas, he studied this reaction, and he found that essentially using an amino-indinol derived N-heterocyclic carbene or triazolium derived carbene generated from potassium terbutoxide as a base, we could generate the dihydroquinoxylene derivatives in up to 98% yield and 98% E. So this was quite interesting because this is the first time an imine was used for excuse me, an aldimine was used as a for the generation of this Brislow intermediate and also as an acceptor for the deoxy-Brislow intermediate generated. So this reaction also found to be working quite nicely with broad scope. I'm just showing selected examples of the dihydroquinoxylene synthesis. And so far I have told you about the chemistry of N-heterocyclic carbenes. So the chemistry of N-heterocyclic carbenes for the umpolung transformation, starting from the well-known concept of carbene catalyzed umpolung of aldehydes to Michael acceptors, and also our studies on the umpolung of aldimines for the synthesis of 2,3 disubstituted indoles, then quinolines, and dihydroquinoxylane derivatives in highly enantiomerically pure form. So far we saw the carbene catalyzed umpolung transformation, or the reactions where the polarity reversal is happening. So the next half of my talk, I will be focusing on another important aspect of carbene catalysis, where this catalytically active species is useful for non-umpolung transformation, where there is no polarity reversal happening. So one such intermediate is the alpha-beta unsaturated acyl azolium intermediate. So this can be generated from a wide variety of aldehydes, acid derivatives. So starting from the alpha-beta acid derivative, acid fluoride or ester, or even free carboxylic acid, the addition of carbene to this acid fluoride can lead to the elimination of this fluoride and lead to this intermediate. And likewise, a series of aldehyde derivatives, in some cases under an external oxidant is required, but otherwise one can start with an oxidized enal substrate without the aid of oxidant. In all these cases, this alpha-beta unsaturated acyl azolium can be generated in solution. And we can see that this alpha-beta unsaturated acyl azolium is electrophilic at the carbonyl position as well as at the beta position. So this is a bis electrophilic species. So one can easily intercept this bis electrophilic species using a bis nucleophilic species at the beta position, a Michael type addition, and the addition at the carbonyl position to eliminate the free carbene, thus leading to the formation of a cyclic compound in majority of the cases. So the beauty of this reaction is, if one starts with an enantiomerically pure carbene for a given transformation, one can have perfect control of the enantioselective outcome of this reaction, or we can have chiral compounds as a result of this transformation. So this concept was already known before we started working in this area. As early as 2010, Armido Studer from Münster, he demonstrated this concept, the addition of a carbene generated from a simple triazolium salt. This carbene can add to this aldehyde, and then this aldehyde is the resultant tetrahedral intermediate is oxidized using this Karash oxidant, this big bisquinone oxidant, a 2-electron oxidant, to generate the alpha-beta unsaturated acyl azolium intermediate. And once this acyl azolium is generated, this can be trapped by a bis nucleophile, a bis acetyl acetone in this case, which having 2 protons, and this could result in the formation of a CC bond and a CO bond to construct the dihydropyranone derivative. So this reaction, although known, there is no asymmetric version known in 2010, and this is applicable only to oxygen heterocycles, and one has to use a stoichiometric amount of this Karash oxidant. So without having any knowledge on asymmetric catalysis at that time, we started our studies by repeating this Studer-on reaction using a chiral carbene. As Shantivardhana Reddy, a talented PhD student in my group, he was able to generate or develop a unified strategy for the synthesis of dihydropyranones and dihydropyridinones by using an oxidized enal and either a 1,3-dicarbonyl or an enamide as a source of nitrogen for the construction of dihydropyridinone using a chiral N-heterocyclic carbene. And we were able to get the product in up to 96% yield and 99% EE. So this was the, again, the racemic version of this reaction was known by Studer himself. So we studied the enantioselective version of this reaction using a chiral N-heterocyclic carbene. So with these results, we were excited at that time, and Shantivardhan was able to demonstrate this chemistry with a wide variety of bis nucleophiles by changing either this 1,3-dicarbonyls or enamide. So he used the enolizable aldehyde, again a bis nucleophile, for the synthesis of 4,5 disubstituted dihydropyranone derivative in up to 99% EE. We also used cyclic analogs such as coumarin derivatives or quinolinone derivative, where tricyclic derivatives are formed in reasonable EE value up to 93% yield. And we also use the pyroxalones as the bis nucleophile for the construction of dihydropyranone fused pyrosols in giving the product in very high yield and enantiomer selectivity. So the underlying principle behind most of this reaction is the abstraction of the proton by the base from the imidazolium or this triazolium salt to generate the free carbene. And the free carbene adds to the aldehydes to generate a tetrahedral intermediate, which undergoes a proton transfer to form the Breslau intermediate. Now the Breslau intermediate undergoes a debromination to generate the key alpha beta unsaturated acyl azolium intermediate. And as I told you, this is electrophilic at the beta position as well as at the carbonyl position. So we have a bis nucleophile, either the 1,3-dicarbonyl or the enamide. So initially the bis nucleophile will add to the beta position in a Michael type addition, generating a new carbon-carbon bond. And this intermediate can undergo a proton transfer, and which is further followed by a nucleophilic acylation to form the product with the release of free carbene, and we get the dihydropyranone or dihydropyridinone product. In addition to providing an insight into a broad scope synthesis of the 6-membered heterocycle, we also found that using DFT calculations done by Kumar Vanga, my colleague from NCL, and he found that this addition of this bis nucleophile indeed take place from the bottom phase of this alpha beta unsaturated acyl azolium, thereby taking this phenyl up, and this is stabilized by an intramolecular hydrogen bonding, which is not possible where the nucleophile adds from the top phase of the molecule to make this aryl down. So thus we can give some insight into the observed enantiomer selectivity of the process by doing computational calculation done by Kumar from NCL Pune. So we are excited with this initial results. So far we were able to trap the catalytically generated alpha beta unsaturated acyl azolium generated from carbenes and a wide variety of enols and acid derivatives. We used enols in most of the cases, so we could trap it with 1,3-dicarbonyls, enamides, enolysable aldehydes, coumarin derivatives, and pyroxalones. So we envisioned, can we use this concept for the functionalization of a sp3 benzylic CH bonds? So this was the idea. We started with a toluene derivative, and the idea is to functionalize the CH protons by using carbene catalysis. And we need to have an enone moiety, a Michael acceptor moiety. And the concept was to add this to alpha beta, or simply enol cinnamaldehyde derivative using carbenes and an oxidant. And obviously these reactions proceed via the alpha beta unsaturated acyl azolium. So initial event will be under basic condition, the base can abstract a proton, and this intermediate will add to the alpha beta unsaturated acyl azolium, and which will be a simple Michael addition constructing a new CC bond. And in this process, the enolate thus generated can come back, and this enolate can add to the enone Michael acceptor by doing a second Michael addition for construction of a new carbon-carbon bond. And then this O- can eventually add to this carbonyl to eliminate the carbene to construct a carbon-oxygen bond. So a Michael lactonization cascade leading to the formation of a tricyclic unsaturated lactone. This was the idea which was realized by Subrato Mukherjee in our lab in 2018. A variety of toluene derivatives, or specifically orthosubstituted enone derivatives, were coupled with alpha beta unsaturated aldehyde using chiral and heterocyclic carbene catalysis to form a variety of tricyclic delta lactone derivatives having 3 contiguous stereocenters in high diastereo selectivity, moderate to good yields, and excellent enantiomer selectivity in most of the cases. So this was exciting. So the carbene catalyzed functionalization of an sp3 CH bond. It is not a CH activation. It is just a CH functionalization via a cascade process comprising of Michael lactonization sequence. So I should confess that in all these reactions, we need to have highly electron withdrawing group on the benzene ring to enhance the acidity of the CH proton so that this facile Michael addition will initiate the reaction. So in the absence of this electron withdrawing group, this reaction does not work. This is considered to be a serious limitation of the method. So with this result, we thought, can we extend this Michael lactonization cascade to an Asa-Michael lactonization cascade? So the reaction is initiated by an Asa-Michael reaction instead of a simple Michael addition. So again, Subrata Mukherjee, my student, started off. He designed a substrate, a Michael acceptor, an indole derivative with a free NH having an enone moiety at the 7th position. The idea was the same, use alpha beta unsaturated acylosolium chemistry. But in this case, this reaction is initiated by the acidity of the NH proton. So a simple Asa-Michael addition will start, which will be exemplified by the presence of an electron withdrawing group at the 3rd position for a facile as Michael addition. So constructing a CN bond. And this enolate thus generated again will add to this enone moiety at the 7th position in a second simple Michael addition and a lactonization via a CO bond forming reaction. And this could be very interesting because in one step, one can access to a variety of pyrroloquinolines in high in-situ selectivity. Again, Subrata Mukherjee, so he realized it in 2018, a variety of indole derivative having an enone tether at the 7th position were coupled with enols for the construction of tetracyclic pyrroloquinoline derivatives. As you can see, this reaction proceeds with high diastereoselectivity, moderate to good yields, and in-situ selectivity in all the cases. So we have demonstrated the benzylic sp3ch CH bond functionalization. So now we envisioned, can we use this strategy for the functionalization of an sp2ch bond in a heteroarene? So the idea was to use a benzofuran or a benzothiophene, so X is equal to oxygen or sulfur, to functionalize the C2 position of this heterocyclic system with the aid of NHTS or amine as a directing group for a functionalization at the C2 position of this benzofuran using carbene catalysis. So we envisioned that using bromoenol and carbene, one can generate this alpha beta unsaturated acylosolium. And once this alpha beta unsaturated acylosolium is generated, we have the benzofuran substrate. The hard center, the nitrogen centered nucleophile, will add to the hard nucleophilic center of this alpha beta unsaturated acylosolium, thus generating an allyl alcohol intermediate, which is poised for a 3,3 sigmatropic rearrangement and Asa-Claisen rearrangement. And now, once the Asa-Claisen rearrangement happened, it can undergo a tautomerization to form an amine or enamine specifically, which can add to this azolium in an intramolecular fashion to leave the carbene, a lactomization. And in the presence of methanol, one can easily cleave the lactone carbonyl to form a free amine with a functionalization at the 2 position. So this was demonstrated or realized by Shilpa Barik, a PhD student in our group last year. So we found that a series of benzofuran derivatives as well as benzothiophene derivatives can be coupled using bromoenols using N-heterocyclic carbenes for an efficient C2 functionalization with very high in-situ induction at the C2, this functionalization at this position. And you can see the products were formed in majority of cases, very good yield and reasonable in-situ selectivity. And for the functionalization of not only benzofuran derivative, but also benzothiophene derivatives. So far we have seen the interception of this azolium species with the bis nucleophiles, such as the coumarins, enolysable aldehydes, and pyrrosol derivatives. So we now thought, can we extend this concept to a 1,3-diox ester, where you have a substituent at the alpha position, where the functionality is no longer a bis nucleophile, like in the case of a simple malonite derivative. So the idea was to use a malonate derivative such as this, which is connected to a ketone by a single carbon tether. And we believe that under basic condition, the deprotonation of this malonate derivative will happen, and this can add to the alpha beta unsaturated acyl azolium, generating an enolate, a carbene bound enolate intermediate. Now this enolate can add via an intramolecular aldol reaction to form this alkoxide derivative, which can undergo a beta lactonization to form the beta lactone, which under the reaction condition probably can decarboxylate to form the cyclopentene derivative. So this was the idea which was realized by Shantagopal Mandal a few years ago in our lab, and he found that a variety of malonate derivatives can, as well as bromoenols, are well tolerated under the reaction condition, and this afforded a series of cyclopentene derivatives. We can see in most of the case the EE values are more than 99%, so high enantiomer selectivity in this process. So where the reaction proceeds via a Michael aldol beta lactonization decarboxylation sequence. So with this result, we thought we can extend this concept to a cyclic beta keto amide, such as this species. Again, this is a bis nucleophile, so a bis nucleophile from this carbon center and the NH center. And again, the idea was to intercept this species with the alpha beta unsaturated acyl azolium, thus generating an enolate intermediate. As if you remember, in the previous case, this enolate was undergoing an intramolecular aldol reaction, but in this case, it undergoes a proton transfer to form this intermediate, which can undergo an intramolecular cyclization to form a glutaramide derivative, the spiro-glutaramide derivative having two chiral centers. And this was also realized 2 years ago in our lab, and a variety of spiro-glutaramides were synthesized by Shantagopal Mandal, and you can see the diastereoselectivity is reasonable, enantiomer selectivity is quite high, and the yields are moderate to good in most of the cases. So far I told you about the interception of this azolium species with 1,3 dicarbonyls or enolysable system or simple nucleophilic species. Now we extend this chemistry from a simple enolate chemistry to a dienolate or a Y-analogous system. So we believe that this is a very well-known concept that one can generate a dienolate intermediate from a beta substituted enone derivative. So this is a dienolate which can be easily trapped with electrophile via this pathway. And one can also think of this dienolate under cyclic condition or cyclic substrate. So we came up with a pyrosolenone derivative, which was again synthesized from a pyrosolone with a condensation using acetophenone derivative. And we found, or indeed Shantavardhan Reddy, he found that a series of enols can be coupled with this pyrosolone derivative for the synthesis of a spirocyclohexadienone derivative. And after a series of optimization, we found that the chiral N heterocyclic carbene along with the Karash oxidant can produce this compound in up to 84% yield and 98% enantiomer selectivity. This was quite nice because this molecule contained a spirocyclic system with a spirocyclohexadienone moiety. This was very interesting, and this reaction was found to be quite general with respect to a wide variety of enols, alpha beta unsaturated aldehydes. So we can see the yields are reasonable and enantiomer selectivity is high in most of the cases. And this reaction also works well with a wide variety of pyrosolone. We can vary all the possible positions of pyrosolones, and the reaction was tolerated well, and we got reasonable or high enantiomer selectivity and moderate to good yield in most of the cases. So the most important thing is the mechanism of this reaction, which is appealing to us. So the reaction proceeds via the generation of free carbene from the azolium salt. It adds to the 1,2 addition to aldehyde, generating the Brislow intermediate. This was oxidized by Karash oxidant to the key alpha beta unsaturated acetylsodium. At the same time, the pyrosolone under basic condition generate the dienolate intermediate, and now this dienolate intermediate can add to the azolium species via a 1,4 addition to form a new carbon-carbon bond. And now under basic condition, it can form a second dienolate. And this is again a second dienolate intermediate. A dienolate addition could result in a 4-membered ring, but at the same time, an enolate addition would lead to a 6-membered ring. So an enolate attack is facile, which lead to the formation of a spirocyclic compound, which gets oxidized to the thermodynamically more stable cyclohexadienol derivative. So we also extended this concept to the desymmetrization of 1,3-diketones. Again, the idea was similar. So generate the alpha beta unsaturated acetylsodium using carbene catalysis and desymmetrize this enol, which is initiated by an Michael addition to the catalytically generated alpha beta unsaturated acetylsodium, and followed by an aldol and a decarboxylation could result in the formation of a tricyclic beta-lactone in high diastereoselectivity and moderate to good yield and enantioselectivity selectivity. So the reaction proceeds via the generation of free carbene, which adds to the enal in a 1,2 addition to form the key alpha beta unsaturated acetylsodium, and now a Michael addition from this deprotonation of the CH proton. So this establishes a new carbon-carbon bond, and this is followed by an intramolecular aldol reaction. So forming this alkoxide, which can undergo a beta-lactonization to generate the product with the elimination of the free carbene. So the second part of the talk, I was able to give you a take-home message on the rich chemistry of a single intermediate in carbene catalysis. So the alpha beta unsaturated acetylsodium intermediate, one can intercept with a wide variety of bis nucleophilic species to form a variety of heterocyclic compounds starting from pyrosolone, pyranone derivatives to pyrosols, the carbocyclic systems, and even the spirocyclic compounds and tetracyclic compounds, with the use of a single carbene bound intermediate, which is the alpha beta unsaturated acetylsodium intermediate. So we were also able to summarize the use of this intermediate, this alpha beta unsaturated acetylsodium intermediate, which shows striking similarity with another key intermediate in organocatalysis, which is catalyzed by a wide variety of secondary amines, such as proline derivatives. So which could add to a variety of enols, generating the alpha beta unsaturated iminium species. And we summarize the similarity of this iminium and azolium in organocatalysis. And this was just out for publication. And also in another phase of our work, we are working on benzene chemistry. We also summarize the striking similarities of benzenes with donor acceptor cyclopropane. So instead of the use of this carbon triple bond in various carbon heteroatom bond forming reactions and cleaving this CC bond of a donor acceptor cyclopropane, which is under strain for various applications in organic synthesis. This was achieved with the help of my colleague, my friend Daniel Wirtz from TU Braunschweig. So in the last 40 minutes, I hope I was able to give you a take-home message on the rich chemistry of N-heterocyclic carbenes, starting from the application of carbenes in organocatalysis, the Umpolung mode of reactivity, the Umpolung of carbenes, the Umpolung of aldehydes, essentially, so which was extended to Michael acceptors and aldimines. And the second half of my talk, I was telling you, or I was demonstrating how one can use the concept of alpha beta unsaturated acetylsodium in various carbon-carbon and carbon heteroatom bond forming reactions for the synthesis of a variety of heterocyclic compounds as well as carbocyclic compounds. So with the help of leaders in the field of NSE organocatalysis, we were able to edit a book on the application of carbenes in organocatalysis. This book is out and it is available in Amazon. I request all of you to have a copy of this book. As you can see, the leaders in this field of organocatalysis has contributed a chapter to this book. So this book, I'm sure this book will give you a lot of information on application of carbenes in organocatalysis. Moreover, we have summarized the activities in the area of benzyne chemistry in the form of another book. Again, you can see the leaders in this field of organocatalysis or this benzyne chemistry has contributed a chapter. This book will be available in Amazon from 2021 June onwards. So I request all of you to have a look at this book when it is online. So the work I have showed you today, this was all did by my PhD students, my extremely talented PhD students, motivated and highly hardworking students. So I'm really happy or blessed to have highly motivated students who did all the job. And I should thank the students Shantivardhana Reddy, so he is working with Uttam Tampar in Texas at the moment. Then Atanu Patra, he's a Humboldt Fellow with Daniel Butts, Shanti Gopal Mandal, Subrata Mukherjee and Tamal Das. So I highlighted most of their works. So Subrata Mukherjee is here. The rest of the students are focusing on benzyne chemistry, and this is the present group size. So Argo is working on carbene catalysis. Abhishek is working on iron chemistry. Sayanshi working on again carbene catalysis. Balana, Tamal left the group. He's now in Rice University, and Subrado and Rahul are working in the area of benzyne chemistry. Tony left the group last year, so the only student from Kerala. He's now at Cologne using postdoc. And this is a familiar face for many of you. So Malini George, who joined our group as a project assistant, she's working very hard from, did her master's from the Department of Applied Chemistry at CUSAT. And moreover, the financial support from various funding organizations, the BRNS, the support from AVH, the startup grant from NCL and IISC Bangalore, the collaborative projects FIPRA, and also the continued support from SERP. And yeah, once again, thank you very much, Dr. Naibin Sebastian, for the very kind invitation to be part of this wonderful event, MATCON Conference 2021. And yeah, to all of you for patiently listening to me. And thank you very much for your kind attention. And I will be very happy to take questions. Thank you very much.
Thank you, Biju sir, for that exciting organic chemistry lecture. You had given a very basic idea of carbene chemistry and heterocyclic carbenes, the umpolong of aldehydes and the generation of Breslow intermediates. Later on, the umpolong, the reversibility of amines, and how this acyl zonium lead to the formation of various heterocycles, the enantioselective synthesis and the various asymmetric catalyzed reactions. That was a wonderful session. Now we'll see whether there are any questions in the chat box. One of the questions from Dr. Ani Deepti. Is the triazolium carbene the only species which can effect these transformations? Or can chiral diaminocarbenes also cause the transformations, maybe with lower yields?
So yeah, Ani, thanks for the question. So the chiral triazolium derived carbenes are well known for enantioselective transformations using carbene catalysis. Yeah, you are right. The carbenes derived from the imidazolium can also be used for the transformation, but the extent of enantio induction compared to the triazole, it is very less for the triazole derived carbenes and the imidazole derived carbenes. And also for introducing the chiral entity for an imidazolium derived carbene is very difficult compared to the triazole derived carbene. So this is also one reason. So the triazole derived amino-indinol derived carbene one can access in 3 steps, but for the imidazole derived species, for the similar carbene preparation, it takes multiple steps. So yeah, triazole derived carbenes are so far good for this asymmetric catalysis using carbenes. I hope I answered. Dipti, is that okay? Or
we'll have some couple of questions from Pradhapan sir.
yes. Hello, sir.
Hello, Biju. That was really nice. Very good talk. Lot of organic chemistry. Very fundamental questions. Very simple.
Yeah.
One of the question is as simple as it can be. What will be the reaction of these NSCs with say nitriles?
Nitriles. So far the carbene reaction with nitriles are not known. One reason could be the less electrophilicity of nitriles.
Okay. It
So
reacts
compared
with
to the imines.
yeah, but it reacts with imines.
Yeah.
Isn't it? Nitrile
Yes.
carbon is certainly more, nucleophilic. Yeah.
I'm not sure. So if you take simple sodium borohydride, it can reduce an imine, but not a nitrile, right?
Okay.
So I think that electrophilicity of the coupling partner also plays a
That may be
major
different.
role. So
Yeah, when you were talking about imines, I was just wondering what will be the situation with nitriles. That's one question.
Nitriles. One reason is maybe it could be possible to have a reversible addition, but in the case of imine, that imine CH proton also plays a role for converting the tetrahedral into
Probably. The kinetics of the reaction is controlling their exchange.
Exactly.
Okay,
Yeah.
you were talking about the synthesis of 2 substituted indole derivatives. Suppose that instead of the aniline derived imines, we use the benzylamine derived imines. In that case, can we go for isoquinolines?
No. So we have tried this reaction because the reaction was giving some, problem associated with this reaction is that the benzylic protons are sufficiently acidic. So this can probably, in one case, we got some Michael type, the Munich type addition to that imine. So a sort of self-addition.
Okay.
So it was not working under the conditions we screened so far.
Or is it that there also the reaction is kinetically controlled? Because in your case, what happens is there's a choice between if it is the reaction is with the alpha beta unsaturated ester component, then we have to go by a 6-member transition state. When it is with the imine, you go by the 5-member transition state. So there may be a kinetic control, 5-member transition state favoring the 6-member transition state. And the compound that I was talking about, when it is benzylamine derived, obviously the choice is between 2 6-member transition states. Is that going to make a difference?
I think the problem associated with this imine, the benzylamine derived imine, aldimine, we have tried to prepare that substrate and do the carbene catalysis, but in few cases, so far we did not get any reactivity. So we tried to form the isoquinoline derivative, but what I feel is that this reaction, the acidity of the benzylamine CH protons, the benzylic CH2 protons, that plays a crucial role in directing the reaction to some of the unwanted products. So in one case,
that may be a serious problem. I think that should be the real reason, acidity of the benzylic.
So we also considered trying to fix that benzyl position with some methyl group. So there, what we faced was the aldimine formation itself was problematic. Okay.
Yeah. And so the final question is, can we do some of these reactions with, say, something like triphenyl phosphine?
Triphenyl phosphine.
Instead of the NSCs, if you use triphenyl phosphine, sort of we are going towards the Bailey-Hillman type of reaction.
Yes. So I feel that phosphines are also nucleophilic enough to add to aldehydes, but mostly these reactions are reversible. And I can promise you that this is not known. The Umpolung reaction, Umpolung mode of addition, or any mode of Umpolung of aldehydes or Michael acceptors is not known with phosphine catalysis. As you rightly pointed out, if phosphine is adding to a alpha beta unsaturated system,
that is where the problem comes. Yeah,
but the first addition happens, but then the proton transfer does not happen. So the functionalization happens from the alpha position, and you get always a Baylis-Hillman type or Rahout-Courier type adduct. So the second proton transfer will not happen to form the Umpolung. Instead, the alpha functionalization will take place. The nucleophile will add, the enolate will directly add from the alpha position without the proton transfer. And it essentially leads to the Baylis-Hillman type adducts or the Rahout-Courier type adducts.
And my final question is, we were talking about CH functionalization of CH3, and you mentioned that the 2 nitro groups are essential there. My question is, suppose that you take a picoline derivative, will it work?
Okay. The picoline derivative,
the picoline proteins, proton should be as acidic as the dinitro-toluene protons, if not more.
Let me think. Picoline, we haven't tried. We thought about it, but the problem we faced was to fix the enone moiety at the 3 position of pyridine. That ended with some issue. Two position we have methyl, and we need a enone at the 3 position, right?
Yeah, that is true.
Yeah, so we ended up with some trouble to install the enone moiety at the 3 position. So this we have tried, but we also tried. So instead of the methyl, we can have the same sort of reactivity instead of the electron withdrawing group or the benzene ring. But then, it is also not a very it is again an indirect method. So we functionalize the methyl with a benzoyl group, an electron withdrawing group. So there we can have this reaction. But the advantage with this method is we can install one more chiral center. So we have 4 contiguous stereo centers. So that works fine. So that project is going on in our lab. Yeah.
Okay, thanks. These are all the questions that I had.
Thank you very much.
Really nice presentation. Good with you.
Thank you very much. Yeah.
We have few questions from Dr. Sindhu Matai.
Hi, Sindhu Ji.
Hi, Biju. First of all, nice presentation, and we are all very happy to attend your very informative talk today. And also, we would like to thank you for giving a chance to one of our students, Balini George, to work with you.
So previously also, so Anu was working with me, so she's now in TU Braunschweig. She's towards the end of her PhD. So yeah.
And I don't have any questions, but I have a doubt for clarification only. For NSC preparation, we have a number of bases. And logically, all the bases can deprotonate the salt and generate the NHC. So is there any criteria for selecting the base? Because all the bases will not work for all reactions, but theoretically, NHC should be generated.
Yeah. This is a very interesting question. So to answer your question, so I have to tell answer that I don't know which base is suitable for which reaction. Because ideally all bases should deprotonate because the carbines are sufficient, the carbene precursors are sufficiently acidic. But in addition to the base, there is also more important we give to solvent for a given transformation. Because in some cases, say if you use ether solvent, the reaction does not work completely, or we have to move to a polar solvent or non-polar solvent. So in that case, the solubility of the base also plays a major role. So we have to switch between inorganic base as well as organic base. So I think so far to my knowledge, to the best of my knowledge, one cannot predict which base is best for a given carbene catalyzed transformation. So what we usually do is with our experience, we start with a particular base, and once we find a reaction or a new observation, we screen most of the base, because we cannot predict which base will give best result. So the only way we can do is perform the reaction in the lab. So yeah, you are right in the sense, ideally all bases should deprotonate the azolium species, but yeah, we cannot predict it, and that's probably one beauty of carbene catalysis, because for each and every reaction you observe, one has to screen, I don't know how many conditions. So we have to consider the carbene first, the base, solvents, then stoichiometry. So the number of parameters are quite enormous in carbene catalysis compared to the other modes of organocatalysis. Yeah. So to answer you in a sentence, yeah, it's very difficult for me to answer.
Okay, thank you.
What we do is we normally screen with the understanding or with the literature knowledge that, say, for example, for a simple stator type reactions, we usually use THF as a solvent. So in those solvents, THF or ether solvents, we have the knowledge that the nucleophilic bases like DBU or even the inorganic base like potassium terbutoxide, they have sufficient solubility to generate the carbene. So these work quite well. These reactions work quite well in these solvents and these bases. So we always start from them, and once we find a reactivity, we screen almost all bases in our lab to get a reasonable or optimized reaction condition. Yeah.
Okay, and one more doubt, is the counter ion also affects the reaction? Like whether it is chloride, bromide, or BF4 minus?
Yeah, in some cases, the counter ion plays a role. It is not a huge difference in reactivity, but there are some cases like chloride as a counter ion. So this chloride also can act as a base to deprotonate. So it is also known that carbene catalysis is known without the use of an external base. So if you use a imidazolium salt with a chloride as a counter anion, the chloride by itself can deprotonate and initiate the reaction. Okay. Once the initiation happens, then the reaction will be always directed towards the forward direction. Other than that, there is not much role, but the counter ion plays a major role for stabilizing the azolium salts, because in some cases, otherwise azolium salts are hygroscopic or air instability or moisture stability. So one can play around with this counter ion to have a stable precursor. Yeah.
Okay, thank you, Biju.
Yeah.
Thank you.
In the chat box, Dr. Mahesh Hariharan has commented, excellent talk, great work. One more question is there from Dr. Ani Deepti. What about isotin-derived enal reactions?
Isotin-derived enal reactions. So these type of enal reactions are quite known. So I hope, sorry. I hope you are dealing with this type of enals, right, Deepti?
Actually, I don't know whether I'm audible. Can you hear me?
Yeah.
I was just to see the spiroxindole, whether you can create spiroxindole.
Yeah. So this the beta reactivity of so this is considered as a beta disubstituted enal derivative. So it is very difficult to functionalize using carbene catalysis at the beta position for a beta disubstituted system. But these isotylidines are exceptional because it is having an amide functionality, which also makes it very reactive at this beta position. So this is quite known, Deepti, this isotin-derived enals. Yeah.
Okay. Thank you.
there is one more comment from Dr. Sumaya. Your talk
Okay.
was very informative, interesting, and very well presented. Thank you very much. So,
Thank you very much. Yeah.
so
Thanks.
I think there are no more questions. So we'll wind up this session. I thank you, Dr. A.T. Biju, for the wonderful presentation and the interaction. Thank you.
Thank you very much. Thank you once again for the invitation. And yeah, it would have been nice if I come physically there, but we have to understand the present situation. So yeah, it was wonderful. Thank you very much.
Thank you, Biju sir, for the nice lecture. Next, we have the oral presentation of OP08, Sajil Kumar Patra. He lost his connection while presenting earlier. For that, I welcome Dr. Leena R for chairing the Sajil's oral presentation.
Hello. So we'll continue the oral presentation. Hello. We'll continue the oral presentation.
Yes.
It is by Sajal Kumar
my
Patra from Niser, Bhubaneswar.
Yes.
The topic is synthesis of urea derivatives via reductive carbon dioxide fixation into contracted porphyrin analogs.
Good noon, everybody. Now I am going to, can you hear me? Hello. I am audible?
Yes.
Hello.
Yes, you are audible.
Good noon, everyone. Good noon, everybody. Now I am going to present oral presentation entitled as synthesis of urea derivative via reductive carbon dioxide fixation into contracted porphyrin analogs. Before going to the main topic, I will briefly discuss about the porphyrin and what are the contracted porphyrin analogs. Porphyrin are naturally occurring tetrapyrrolic macrocycle where the 4 pyrrole rings are connected by sp2 hybridized carbon atom, that is methane base, and these are 2, 3, 7, 8. These are the beta position, 5, 10, 15, 20. These are the meso position, and 1, 4, 6, 9. These are the alpha position of porphyrin. Actually, porphyrin is 22 pi electron system, but only 18 electron in shortest conjugation, owing Huckel rule of aromaticity. Now, what is contracted porphyrin? Contracted porphyrin analogs are those compounds containing at least one carbon less than that of porphyrin. These are the contracted porphyrin analogs: subporphyrin, isocorol, subporphyrin, norcorol, and corol. But our region of interest is the corol. So what are corol? Corol are aromatic tetrapyrrolic macrocycle. It is also 18 pi electron aromatic system. It has one carbon atom short than that of parent porphyrin. That is C19 is absent here. That's why it's Br direct pyrrole bond. It also stabilizes the metal ion with high oxidation state. UV visual spectra of corol is also similar to that of porphyrin, but compared to porphyrin, here one less Q band is observed in 500 to 600, around 500 to 600 nanometer. Our research interest is to design synthesis and characterization of bleached corol and metarocorol compound and its necessity modification. Synthesis of relevant metarocorol complex whose oxidation level, electronic property, and mode of reactivity can be tuned by selective introduction of suitable donor or acceptor group in the corol framework. Knowledge about different functional and biological system by synthesizing different model system. Now come to my present work. In this recent work, carbon dioxide gas from ammonium carbonate is trapped by previous corol with the help of two adjacent NH, that is N21 and N22 nitrogen atom, to form carbamide corol derivative. This type of N21-22 carbamide corol derivative was first reported by Gross et al. In 1999, but in their synthetic procedure, the main limitation is they used phosgene as a carbonylation agent, which is very much toxic and poisonous gas. But in the recent work, we present a new synthetic protocol which is relatively greener. Here, previous corol, upon treatment with ammonium carbonate at 110 degrees centigrade temperature in DCM pyridine mixture leads to the formation of carbamide corol derivative. This is the proposed mechanism for conversion of corol, previous corol to corresponding carbamide corol derivative. In order to generalize the newly synthetic protocol, we have explored a series of differently substituted coral ligand functionalities bearing electron donating as well as electron withdrawing ligand group in the coral periphery. And it is shown that this method was applicable to large variety of FB coral and the yield of the product is also very good. These are the isolated yield of different coral carbamide derivative from the starting coral. The 1A to 7A, these are the FB coral, and 1B to 7B, these are the carbamide coral derivative. All of these newly synthesized N2122 carbamide coral derivative has been thoroughly characterized by using various spectroscopic technique, UV visible IR, NMR, emission, mass spectra, and finally by crystal structure. First, these are the UV visual spectra of 1B to 7B. The absorption spectra of 1B to 7B in toluene is similar across the series, but these are the significantly different from that starting coral. Compared to the starting coral, one extra Q band is observed here, and also blue shift of the Soret band and Q band also occurs here. These are the IR spectrum, and this type of blue shift occurs due to this carbamide coral. We think this type of carbamide coral derivative structure, carbamide coral structure. The FTIR spectrum of 1B to 7B are shown here as KBR plate shows the peak at 722, 740 semi-inverse due to CO group stretching. The NMR spectrum of 1B to 7B exhibits sharp peak in accordance to the aromatic proton in the region of 9.7 to 7.6 ppm. It also observed that peaks are descended by near about 0.7 ppm in this is in the carbamide coral derivative compared to the previous coral. These are the 13C NMR of 1B and 5B. Electron emission spectrum of all the compound are similar type, and where we excited the compound in the Soret band, electrochemical mass spectrometry also shows that the 1B comes at m by z is equal to 552.2 in CH3CN, and also these are the isotopic distribution of mass spectra. The crystal structure of 3B, 5B, and 7B are shown. One of the representative at 7B we'll discuss. The crystal system of 7B is monoclinic, and unit cell has four 7B molecules. We also perform DFT geometry optimization and frequency calculation. The DFT calculated bond distance and bond angle matches nicely with that obtained from the XRD value. In case of 7B, the carbon atom of CO moiety deviates from the mean N4 coral plane by a distance of 0.648 Armstrong and gives rise to a domate conformation. And the pyrrole ring nitrogen atom deviates from 19 carbon atom mean coral plane by a distance ranging from 0.229 Armstrong to minus 0.226 Armstrong in case of 7B. And also CO bond distance of 7B in XRD calculation we get in XRD we get 1.21 Armstrong, whereas by theoretical calculation we get it 1.208. So this is also in agreement with experimental finding. Whereas in case of urea, the CO distance is 1.26 Armstrong. The theoretical UV visible and IR spectra also complement the experimental data nicely. Here the IR spectrum experimentally recorded FTIR spectrum in the red line, whereas in case of this red line is experimentally obtained, and this black line is from the DFT calculation, and these are also matches nicely. And the UV visible spectra also complement to experimental data also. Here we present in case of 1B, the CO stretching frequency is 1736 semi-inverse. Experimentally we get, in theory
Hello.
Typically, we get 17.
Sajal Kumar,
UV
your
visible
time
in case of UV visible
please wind
spectra.
up.
Yes.
Your time is over.
Hello?
Please wind up.
Conclusion, in summary, we have.
Hello, can you?
Hi, yes, yes, ma'am. Hello. Hello.
Yes, your time is over. You just wind up. That's all.
Yes,
Hello,
thank you.
can you hear me?
Yes, yes,
Oh,
ma'am.
you can say the conclusions. You can say
Yes,
the
yes.
conclusions.
In summary, we have developed an efficient, mild, high-yielding and single-step methodology for facile synthesis of N2122 carbamide coral derivative without using any toxic element. Urea-based system has shown interesting biological system. Thus, it is logical to consider that novel carbamide coral derivative and their possible metal complex can be utilized in future for as a potential agent in medicine for detection or in diagnostic purpose. Thank you.
Okay, Sajal. So you had prepared various coral systems, right?
Yes, yes, ma'am.
And how the UV visible spectra of this coral is different from porphyrin?
Actually, UV visible spectra of coral and porphyrin are similar type, but only in case of coral, there is in case of porphyrin, 4 Q band observed in 450 nanometer to 700 nanometer, whereas in case of coral, only 3 Q band is observed.
2 or 3 in coral?
In coral, 3 Q bands.
3, okay. And the emission peak, how many emission peaks did you obtain? You recorded the emission corresponding to the excitation of in the SORAD band only?
SORAD band only, ma'am. Only in SORAD band we excited the molecule.
And the title of your presentation is Synthesis of Urea Derivatives via Reductive Carbon Dioxide Fixation. So how was this carried out? How much time carbon dioxide was purged, or
no, ma'am,
how the reaction was carried?
Ma'am, only purging CO2, the reaction does not go, because we think that insolubility of CO2 in our reaction mixture is the responsible for that. Only if we use any CO2 generating agent like any carbonate or bicarbonate and heated it 100 degrees centigrade, only we get that time we got this carbamide coral derivative. Because in as it
whether we have to control the pressure of purging of CO2. Hello? Hello? I think Sajal Kumar has lost his internet connection, so we'll wind up the session.
Thank you, ma'am, for chairing the session. Here we are coming to the end of this session. The afternoon session is Professor K.K. Mohammed Yusuf Endowment Lecture at 2 p.m. For the kind attention of attendees, the link to join the endowment lecture is provided in the MATCON 2021 website. All are requested to join in the corresponding link. For the session 3 at 7 p.m. IST, all are requested to join back in this link itself. Everyone, please try to join 10 minutes before each session. Thank you.
Hello. Hello. Sorry, ma'am. I have also lost the connection.
Okay, so I hope you heard the question, right?
Yes, ma'am. Actually, by purging CO2 gas in this medium, the reaction cannot initiate, because I think this is for insolubility of the carbon dioxide gas in the reaction medium. I think so.
Okay.
But when we used any CO2 generating reagent like carbonate, bicarbonate, and heated it, then only this reaction is successful.
Okay, Sajal.
Any question, ma'am?
No, we don't have any more questions. We are winding up the session.
Yes, ma'am.
Okay, thank you, Sajal.
Sorry for this disconnection for 2 times.
Okay, thank you, Sajal. We have one more announcement.
Yes.
After the endowment lecture, there is poster presentation at 3 p.m. For all the participants, the corresponding link will be given to their mail. All are requested to join at 3 p.m. itself. Thank you, everyone.
Yes, ma'am. Thank you. Can I leave?
Sajal, you can leave.